Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to briefly discuss on pulse code modulation. Modulation is defined as the process of modifying the properties of the carrier signal such as amplitude, phase or frequency based on the information bearing signal. So, pulse code modulation is a method that is used to convert an analog signal into a digital signal so that a modified analog signal can be transmitted through the digital communication network. PCM belongs to a class of signal coders known as waveform coders. PCM systems are complex in that the message signal is subjected to a large number of operations. The essential operations in the transmitter, receiver, and the communication channel are displayed in the diagram here. The sampling, quantization, and encoding operations are commonly performed in the same circuit, which is called an analog to digital converter. Regeneration of impaired signals occurs at intermediate points along the transmission path, which is also the channel, as indicated in the diagram here. At the receiver, the essential operation consists of one last stage of regeneration, followed by decoding, then demodulation of the train of quantized samples. The operations of decoding and reconstruction are once again usually performed in the same circuit called a digital to analog converter. When time division multiplexing is used, it becomes necessary to synchronize the receiver to that of the transmitter for the overall system to operate satisfactorily. Let us now discuss each of these blocks in brief detail. As we can see, we have at the very input a source of continuous time message signal, which is an analog signal. This is first and foremost passed through a low pass filter, which also acts as a pre-alias filter to make sure the input signal is strictly band limited at the output of the filter. This is then fed to the sampler. So let us now discuss about sampler. The incoming message wave is sampled with a train of narrow rectangular pulses. In order to ensure perfect reconstruction of the message at the receiver, the sampling rate must be greater than twice the highest frequency component of the message wave. This is in accordance with the Nyquist theorem. In practice, as I already have stated, a low-pass pre-alias filter is used at the front end of the sampler in order to exclude frequencies greater than W, where W is the cutoff frequency of the pre-alias filter. The use of pre-alias filter allows us to convert the input signal into a strictly band-limited signal, which is going to help us a lot in avoiding aliasing. Thus, the application of sampling permits the conversion of a continuously varying message wave to a set of discrete samples. Moving on to quantization. The definition of quantization is the conversion of an analog or continuous sample of the signal into a digital or discrete form, and this process is called as quantization. Graphically speaking, the quantization process creates a transfer characteristic that is staircase-like in appearance. In simple words anyhow, the quantization process has twofold effect. The first one is the peak-to-peak range of the input sample amplitudes is subdivided into a finite set of decision levels or decision thresholds. Secondly, the output is assigned a discrete value selected from a finite set of representation levels, also called as reconstruction levels, also called as quantization levels. In the case of an uniform quantizer, the separation between the decision thresholds and the separation between the representation thresholds of the quantizer will be a common value, and this value is called as the step size. Moving on to the encoder. The output of the quantization is a set of samples, each with a discrete amplitude level. To transmit these amplitude levels through the channel requires representing the discrete set of amplitudes as a particular arrangement of discrete events, which is called as a code. One of the discrete events in a code is called a code element or symbol. A particular arrangement of symbols or code elements used in a code to represent a discrete amplitude at the output of the quantizer is called as a code word. For example, in a binary code, each symbol may be either of two distinct values, such as the presence or absence of a pulse. The two symbols of a binary code are commonly denoted as 0 and 1. In a ternary code, each symbol may be one of the three distinct values, and so on for other codes. Assume that each code word in a binary code is made up of n bits, small n bits. Then, using such a code, we may represent a total of 2 to the power of n distinct numbers. The code words are then represented using a suitable signaling scheme to enable transmission through the channel. So, the output of the encoder is the pulse code modulated wave, and this waveform is now applied to the channel. The channel, you should note, is made up of a large number of regenerative repeaters. So now let us discuss the regenerative repeater in brief detail. The most important feature of the PCM system is its ability to control the effects of distortion as well as noise produced by transmitting the PCM wave through the channel. This ability is accomplished by reconstructing the PCM wave by means of a chain of regenerative repeaters located at sufficiently close spacing along the transmission path. Let us look into what a regenerative repeater is made up of. Right, as shown in this diagram here, a regenerative repeater performs three basic functions, namely equalization, timing, and lastly decision making. The equalizer is used to shape the received pulse in order to compensate for any of the effects of either the amplitude or phase distortion produced by the channel. Then, the timing circuit provides a periodic pulse train for sampling the output pulses of the equalizer at the instance of time where the signal to noise ratio is maximum. The decision device then takes these pulse amplitudes as input and compares them with the threshold value. If the pulse amplitude is greater than the threshold value, then the decision is made in favor of symbol 1 and vice versa. Since we have considered a binary PCM system with on-off signaling scheme, the repeater makes a decision in each bit interval indicating either the presence or absence of a pulse. If the decision is yes, in the sense if the pulse is detected, then a clean new pulse is transmitted to the next repeater. If on the other hand, the decision is no, which means the absence of a pulse, then a clean baseline is transmitted. In this way, the accumulation of distortion as well as noise in a repeater span is completely removed, provided that the disturbance is not too large enough to cause an error in the decision-making process. This in fact forms the most fundamental idea behind the success of PCM. In simple words, every single repeater is going to analyze the received distorted PCM wave and is going to create a completely new PCM wave based upon the decision device. In practice, however, the regenerated PCM signal may depart or may differ from the original signal in two main aspects. The first one is the presence of noise as well as interference causes the repeater to make wrong decisions occasionally, thereby introducing bit errors into the regenerated signal. Secondly, if the spacing between the received pulses deviates from its assigned value, then a jitter is introduced into the regenerated pulse position, thereby once again causing distortion. If these two effects can be minimized, then the PCM will provide a very high efficiency of transmission. Let us now go back to the receiver part of PCM. The very first process in the receiver is one last stage of regeneration. That is, we are going to use one last regeneration circuit, which in fact produces clean pulses at the output of the regenerative circuit, and these pulses are then regrouped into code words and then decoded or simply mapped back to create a quantized signal at the output of the decoder. Then we have the reconstruction. The final operation in the receiver is to recover the analog signal at the output of the decoder. This is done by passing the decoder through a low-pass reconstruction filter whose cutoff frequency should be equal to that of the highest frequency content of the input signal, which is represented by W. Assuming that the transmission path is error-free, the recovered signal includes no noise, with the exception of the initial distortion introduced by the quantization process. This signal at the output of the reconstruction filter is then passed on to the final destination. This is about the discussion on the blocks of a PCM system. Additionally, If you remember, when we were discussing pulse amplitude modulation, we said it is possible to perform time multiplexing of the input signals, thereby saving both time as well as bandwidth. In a very similar fashion, we can perform multiplexing of the PCM signals as well, thereby increasing the efficiency of the overall system. However, the moment you introduce multiplexing into the system, it becomes very essential to introduce synchronization between the transmitter and the receiver. This synchronization is going to make sure that the transmitted signals will be delivered to the corresponding and respective destination users. Right, with that, we come to the end of this brief discussion on pulse code modulation. If you liked this video, kindly press that like button and subscribe to my channel for more videos on digital communication. Thank you for watching. Have a good day.